Hello, everyone. I'm Steph, contributor of the God Network. Today, I'm going to go through the God Network protocol on a leap towards a 2 Bitcoin layer 2 by Bitcoin, by BitVM2. So first, we still need to, discuss some practical question about why we need to build a Bitcoin layer 2. The first is we need to, for most of the DeFi, it cannot be applied on the Bitcoin. So almost a lot of projects are trying to improve the programmability of the Bitcoin. The second one is reduce the gas fee. And the most important is the security inheritance. That means as many talks about the BitVM about their projects, they're always emphasis. I mean the security. Okay, so because almost all of I would say the side system are not designed to level they manage or to secure their system or inherit their the security from the Bitcoin. Okay, so before we go through the God network, I think it's important to recall the BitVM paradigm. Okay, so first, I think many speakers has mentioned one is BitVM is. Here I have a simple summary, and I also have a picture to show how BitVM works. Of course, it's a bridge protocol that's one of an honest assumption. This is very, very important that we need to, as a layer 2, actually, we need to use the layer 1 to verify all the transaction execution or the consensus algorithm or the, every transaction of the layer 2 that's being executed correctly. Okay, so here that's why we always trying to build a more secure protocol. Okay, the second point is because the Bitcoin script is stateless. That means it's done like the smart contract on Bitcoin or on Ethereum. That's you have some storage like map or some other field to to keep track of the state stats. But on Bitcoin, you just have UTXO. If you want to keep track of some stats, you need to use the pre-signed transaction or the one-time signature. And here another important features is the optimistic challenge and response mechanism when you want to trying to do some optimistically execute some computation, and then let everybody can challenge you to verify that your execution is correct. So here an optimistic challenge response is necessary, and a bit of humor also leverage the snag to enable this universal computation. As people said, a snag verifier you may need maybe 2 or 3 pairing. The pairing computation is very heavy. So if we want to implement that with the Bitcoin scripts, we may need a lot of skills, like we need to build a lot of composite opcode, and we need to implement some complex scripts. Okay, so actually that's a picture of how the simplified BitVM protocol works. First, somebody came to peg in that as it's also namely the bridging the assets into your bridge, I would say bridge smart contract or covenant, and then he also needed to get a pre-sign and of entrance signature. And after, okay, this is very important to notice that the private key for the pre-sign of any transaction should be removed immediately to make sure that the protocol can follow the one of any security assumption. Okay, that's the packaging. After you transactions on the static system, if you want to bridge out your assets, here we need to involve the operator. The operator came out to pair the people who want to withdraw, and then he started his we said reimbursement process to get the assets back to the operator. So he kicked off the transaction, and then the kickoff may generate several outputs. One is like the some of these corporate like the first one in 2 weeks, it's a time lock, and we also generate some connector. Connector actually it's you can consider it's a conditional selector. That means if some happy, if some condition happened, maybe the output can be used following up the happy path. If something not good happened, maybe we have another unhappy path to spend that output. Okay, so when the operator kick off the reimbursement process, he need to wait for the challenger to kick to verify his commitment, and then meanwhile, if some challenger takes the like the connector A, he put the connector A, the operator need to submit the transaction asset, the assert transaction, and to commit the execution trace to try to convince or prove his computation is correct. Okay, after that, the tap root in the assert transaction needed to verify that the execution of some points is correct. Of course, for the left side we have two happy paths and one unhappy path. That's okay. Yeah. So regarding this, protocol, actually we still have some open problems right now for all the two Bitcoin layer 2. The first one is, not all people just care about the just know how to verify the proof, but actually, when we begin to verify the proof, we need to commit the public inputs. For example, if we have a such system built on some consensus system, and for the consensus for the such system, it's very easy to fork. But if you just verify the execution layer, it's maybe forked. But if you just verify the the execution layer, but the consensus layer may not work. So for the true Bitcoin, you need to verify both the execution core and the consensus layer. Second point is the layer 2 should be should guarantee the liveness and safety, being independent of the layer 1. And the third point is the real-time proving is not possible yet right today. Okay, so for those different problems, I think God network has its own answer. Let's go to the how to see God network solve those problems. The first is how to solve the Bitcoin transaction introspection problem. For this problem, let's just recall the protocol of the Bitcoin BitVM protocol. You can see that when you peg out the transaction, you probably need to verify that when you kick off the optimistic challenge, because if since all those transactions happen on the layer 1, so on the Bitcoin, so how should we, to verify that the peg out transaction is confirmed is very important. Sorry, this slide is also not the latest one. Okay, so for the latest perspective, I think the first point is verify that the peg out is confirmed. The second point is we need to commit the public inputs of the proof that you are that operator submitted for its reimbursement. Okay, the solution here, I think we have two solutions. I should say, yeah, we have two solutions has been public discussed. The short solution is from Gordon work. The first one is a super block. Yeah, the super block depends on depends on some special OP code like the OP block hash, which is not possible today. The second one is the watchtower. This is proposed by the Satria. It's just to commit additional information by the permissionless watchtower set. Yeah, inspired from that, from this, but this is still not the final, not the final solution to solve our previous problem I mentioned. So that's why we, introduce this decentralized secret-based watchtower solution. Okay, basically it can commit additional information by the watchtower set, and we also replace. We actually will remove the peg out transaction from the BitVM protocol, and then we need to commit the public inputs and of our sockets by the decentralized sequence. Okay, let's dive into the details of our decentralized sequence watchtower solution. So in this algorithm, first the operator may pay out the user by atomic swap. That means we use this mechanism to solve at least two problems. The first, we don't need to conform that's the peg outs because we removed the peg outs. The second one is in the real world use case, we actually may have there may be thousands, maybe hundreds of thousands withdrawals every day for layer 2. So for the if we run it with if we run the BitVM for each withdrawal, it's not practical actually. Okay, so that's why we need to involve with like some atomic swap to first to build the channel between the operator and the user to ask the operator to pay the end user first, and then the operator to kick off the reimbursements for itself. Of course, for this solution, we first burn the wrapped BTC on layer 2 and then generate the proof of the logic, which include, verify the block execution, the consensus, and also the burn transaction. So with this solution, we can, we can simplify the BitVM and make it be more practical. But meanwhile, we don't break any security. We don't compromise any security here because we still just need the assumption that's one honest operator, and the layer 2 consensus protocol here is also permissionless. Okay, so for the security, yeah, as I mentioned, because it's always possible to prove all the latest logic with the bond transaction, and we generate the Merkle proof for the transaction. We also, verify the consensus ladder clients and the EVM ladder clients. So to make sure that's the one of an honest security assumption heard. And this is how the protocol looks like. So here we add some, I would say add about a list of watchtowers here. Now each watchtowers maybe comes from the decentralized sequencer network, and then we the main difference is here. We actually added some new outputs for the kickoff transaction, and those new outputs it's actually determine if we can go to the assert transaction. So when some watchtower comes out to challenge the public inputs, we can if some challenge submit a more difficult block here, he may spawn the outputs that will be spent by the assert transaction. So this is the preferred design. So let's go back to the detail of the secure watchtower mechanism. Here we have a new I would say a list of new precise transactions, like the DCQ challenge and the operator claim, DCQ disprove transaction. Here the first, when the operator submitted the kickoff transaction, he needed to he needed to generate a list of secret. He needed to build like 100 hash log with the watchtowers. He generates the secrets and then publish the hash value of the secret to the different watchtowers, and then he submits the key off transaction and waits for about like half a week to wait for the watchtower to challenge the public commitments transaction with more difficulty block. So if here is the trick is if if some watchtower submits a challenge first, if the operator acknowledges that that's the challenge, he needs to provide the secrets. If he cannot, acknowledge the challenge, he may someone else can submit a disprove, the secret disprove transaction, so it can board the connector S. So make sure this can make sure that the operator cannot start submit the assert transaction here. So if the operator acknowledge the operator claim by the if it's acknowledge the challenge, the operator may need to submit the proof, the longest chain proof, and it's total work. So in the assert transaction, the operator needed to submit the proof, submit the execution trace. In that trace, it should include all the burn transaction, Merkle proof, the execution proof, the consensus net proof, and also including the secrets and some additional information from the acknowledged transaction, and hence if then the assault transaction can be broadcast. If after we submit the assault transaction, when the operator can submit the transaction successfully, we going back to the BitVM protocol then. So being used so leverages this this modification of the BitVM, we can make sure that we can simplify the BitVM of the protocol and leverage the permissionless consensus network to build a real two Bitcoin layer 2. And for the cross-chain atomic swap, actually it's a double HTL hash lock. Okay, so operator, it solves the problem that operator may be not interested in the payout with smaller amounts of BTC, and so we can build the channel between the user and the operator to initiate the HTLC between the God network smart contract and the Bitcoin. So it's very easy to implement that actually, but we still need to keep to guarantee the liveness of the operator when the user really want to to withdraw anytime, anywhere. Yeah. So here we also have some solution like the one-time verifiable encrypted signature, namely the adapter signature, here to solve this kind of problem. Another one is the core of the decentralized sequencer. That's the command BFT. Actually, I think most of the people should have knowledge about the Cosmos consensus. Okay, so it's binding for first tolerance and deterministic state machine replication engine. It's the benefits of the decentralized sequencer including first is eliminates the single point of failure. Second is we can use the slash and incentive mechanism in the command BFT to align the incentive across all the network participants. That means everybody can join, become a validator, and also he also can join, be part of some validator to mining the blocks and to own the gas, and then the gas can be returned to the community users to make a very good circle. And finally, it can also include the liveness of network by security. Okay, so let's just have a conclude about the bridge protocol. The first client's protocol is that how to bridge the assets from the Bitcoin to gold. So for this protocol, the objective of the security is the one of an honest assumption, and this security the basic step including verify the Bitcoin in God's EVM. Okay, so since it's very elastic to write any program on the EVM on God network, so we can use the smart contract to verify the longest chain. Just based on the difficult, it's just the SPV, and then we also use the MIPS to generate the proof of the Bitcoin and to verify the Bitcoin block execution on God network. And another part is the data availability. So it's also very important. When Bitcoin is always alive, so the availability here, I think it's not latest. That's sorry. I mean, here is yeah, we need to verify. We don't need to upload all the transaction from Bitcoin to Go network. But SPV maybe is enough. SPV and it's the execution proof is enough. The ZK. Okay. Yeah, I think another point is how to verify the. Yeah, we have just been playing a lot of the protocols blocks about the BitVM and improve the BitVM version. And the next part is how to verify the the got transaction on Bitcoin. So the first we after the pack-in transactions, I think then the God network. Sorry, some slides not here. So when we talk about the God to Bitcoin protocol, first we use the atomic swap to build a channel between the operator and the user. The user, and then the operator need to kick off the reimbursements by commits the public input first, and then the operator need to kick after. The watchtower challenge process. The operator begin to to submit the to kick off the. Okay, should be the operator kick off the reimbursement transaction, and then the watchdog start to challenge the public commitments, and then after the public input commitment finished, if there's some challenge there, the operator need to submit the execution trace by the by the assault transaction. If the challenge is success, the operator the unhappy pass maybe happen. If there no challenge really happens, the safe part, the happy pass will be go. So okay, so let's go to the third part is what the real-time proving currency is not possible. Is not possible today. But as we I need to say for most of the signing system, actually there are not so many transactions as a Bitcoin. We can see from the yes proof that for most of the transaction, it can already be proved in about 1 or 2 minutes. With the gas, maybe more than 10 meaning. For the gas used for each transaction, it's maybe larger than 10 mini. So if of course currently a lot of the transaction maybe there are no many transactions on the status system, so it's still be possible for us to add scale the proving service horizontally to make sure that we implement the real-time proving. Okay, and for God network, it's employ the ZK MIPS. So we can see that for the ZK MIPS tree, it's can reduce the the proving cost to about 0.4 cents per meaning gas. And here we also leverage a lot of technology, including the Planck 3 pipeline, E2E proving, and the in-parallel batch improver, stack-to-stack recursive proof. Okay, so the final is a summary about one kind of is a summary about the God network. One we want to build for the developers. Okay, so first important is keep guarantee the security, is the security guarantee of the one of an honest assumption, and we provide the true decentralization with the decentralization sequencer and the BitVM bridge, and we also implement the full verification, including the execution layer, the consensus layer, and we also provide a dual, slashing security, includes the slashing and incentive mechanism in the command BFT and all other we are in the improved BitVM protocol. It can also provide the slashable security. Okay. Yeah, thank you. Yeah, that's information about God network. So, yeah, thank you very much.
Thank you so much, Stephen.